Okay, here are the notes for section 10.3, which deals with numerical statistics. So just some definitions to start, parameters and statistics. So numerical summaries of a data set are called statistics. They serve to describe the individuals from which the data come, so the gathering and processing of such numerical information is also called descriptive statistics. The science of statistics comes in when we use descriptive statistics, like the results of a study of 1,500 smokers, to make judgments called inferences about entire populations, like all smokers. Statisticians are really interested in numbers called parameters that describe entire populations. Because it's usually impractical or impossible to measure the entire population, statisticians gather statistics from carefully chosen samples, then use the science of inferential statistics to make inferences. So, you can't go out and measure the height of all people from 20 to 30 to find the average height, but you can take a sample of people from 20 to 30 and average their heights and use that to make an inference about what the entire population would do. Okay. So, for example, one says a 2004 study called All Work and No Play, listening to what kids' parents want from out of school time, reported that 32% of middle school and high school students wished there was an after-school activity that offered homework help. This report was based on a survey of 609 randomly selected students, 6 to 12, had a margin of error plus or minus 4%. Does the study measure a parameter or a statistic, and what does the margin of error mean? Okay. So, what we have here is, since we have a sample, so we have a statistic. So since we have a sample, that means we have a statistic. If you have a population, you have a parameter. Margin of error means that the true value could be essentially extend the range. So 32% of their sample said, so the actual value for the whole population is probably somewhere between 28% to 36%. You would add or subtract the 4%. Because, we sampled a very small group compared to potentially all of students 6 to 12. So that's why we have this margin of error. If you sample everyone, then your margin of error is 0 because you know exactly the answer to everything. Okay. So, describing and comparing distributions. So the shape of a distribution may be unimodal or multimodal, symmetric or skewed, as we talked about in the previous section. The center of a distribution indicates where the typical measurement is. The spread of a distribution tells us whether measurements tend to be close together or vary widely. All right, so first thing, we've got the median. So the median of a list of numbers arranged in order, could be either ascending or descending, is the middle number if you have an odd number of numbers, or the mean of the two middle numbers if n is even. So example 2, find the median of the annual home run totals for Roger Maris's major league career. So what I need to do is I need to order these values. Now it doesn't matter which order I do, it's the same thing. So let's see here, the smallest one is 5. And then we've got 8 and 9. And then 13 would be next. All right, and then we've got a 14. No 15, so 16 would be next. And then for 23. Then 26. Then 28. Then 33, 39, and 61. So there we go. So in order. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers. So I need the middle two. So that'd be 1, 2, 3, 4, 5, 6. These two are the middle two. That's 6th and 7th numbers. So 16 plus 23 divided by 2. So that's going to be 39 divided by 2, which is 19 and a half. So the median number of home runs he hit was 19.5. The number that lies exactly halfway in the middle here. Another definition here, resistant. A statistic is resistant if outliers do not have a large effect. So we've got a 5-number summary. So the simplest and crudest measure of spread is the range, which is the difference between the maximum and minimum values. So just maximum minus minimum. So just as the median separates the data into halves, quartiles separate the data into fourths. The first quartile is the median of the lower half. The second quartile is the median itself, and the third quartile is the median of the upper half. The interquartile range is the difference between Q3 and Q1. So here's your 5-number summary. You list the minimum, Q1, the median, Q3, the maximum. Now, in order to find Q1 and Q3, you have to know what the median is first. So you need to order your numbers, find these 3, then calculate these 2. So find the 5-number summaries for the male and female life expectancies in South American nations and compare it to the spreads. So let's see here. I really don't want to reorder these, but we can do it anyway. So for the men, our list becomes 64, 65, 68, 70, 71, 72, then 3 more 72s, then a 73, 2 73s, and a 76. Didn't leave myself enough room. For the ladies, our list is 69, 69, 74, 74, 78, 78, 78, 79, 79, 80, 80, 81. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 12 numbers. So we need the 6th and 7th. 1, 2, 3, 4, 5. So the median's going to be somewhere between those two. 1, 2, 3, 4, 5, 6, and 7 right there. All right, so for the males, 5-number summary. So the smallest value is 64. The median is halfway between 72 and 72. So that would be 72. And the maximum value is 76. Okay, so to find these values, so my median lies right there. So I break it into the smallest group and the largest group. So the Q1 value is the median of these numbers. So 1, 2, 3, 4, 5, 6. So I need to do the median again. Halfway between 68 and 70 is 69. Same thing up here. 1, 2, so it's halfway between these two numbers. So halfway between 72 and 73 is 72.5. For the ladies, the smallest number is 69. The median is halfway between 78 and 78, so 78. And then the largest number is 81. So to find the Q1 value, so there's my median lies right there, halfway between the two 78s. So there's my middle two numbers, halfway between the 74s, the 74. Here be 79.5. So there you go. Compare the spreads. So let's see here. So the ranges are actually the same in each case. The range is 12 and 12. The interquartile range here is 3.5, and here is 5.5. So the men have a smaller spread. 64 to 76 is much smaller range than 89, so, or for the quartiles. So most of the men are clustered around the center, whereas the ladies is more distributed. Okay, so you can use the 5-number summary to create what's referred to as a box and whisker plot. As a graph that describes, or graphically describes, the 5-number summary. The box plot consists of a central rectangle of the box that extends from the first quartile to the third quartile, the vertical segment marking the median. Line segments are whiskers and extend at the ends of the box towards the minimum maximum, stopping short of any outliers, which are indicated separately. A number in a data set can be considered an outlier if it is more than 1.5 the interquartile range, below the first quartile, or above the third. So when we look at Roger Maris's home run totals, blah, 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 we see that 61 is much larger than any of the others. Is 61 an outlier according to this criteria? So actually here, well, I saved my work. So let's see here. So here was the Roger Maris's in order: 5, 8, 9, 13, 14, 16, 23, 26, 28, 28 again, 33, 39, 61. So list in order. The median was here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. I missed a number somewhere. 5, 8, 9. 5, 8, 9, 13, 14, 16, 23, 26. No, I did 28 twice. Silly me. That guy shouldn't be there. So there, no. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So the median here was 19.5. The maximum is 61. The minimum is 5. So I can find the quartile values here. So 1, 2, 3, so halfway between 9 and 14, or 9 and 13, would be 11. Halfway between 28 and 33, it's not going to come out evenly. That's 61. Half of 61 is 30.5. So the interquartile range is the difference in the two quartiles. 30.5 minus 11, which is 19.5. So any number that is, so an outlier at the top is the Q3 value plus 1.5 times this. So if I take Q3, that's 30.5 plus 1.5 times 19.5. Typed in wrong, 30.5 plus 1.5 times 19.5. So outliers are greater than 59.75 or less than, we do the same thing down here, we subtract from 11 minus 1.5 times 19.5, which is a negative number. So 61 is an outlier because it's more than that value. Okay, draw the box plots for the male and females life expectancy and compare the GPR from the previous example. Let me find that work. So what that would look like, so for the males, what we would do is, actually we'll put them on the same axes. We'll try to. So the smallest value I have in the list was 64, the largest value is 81, so we'll count by twos, 66, 68, 70, 72, 74, 76, 78, 80, 82. So for the men, so we have 64, the lowest value. 69 was their Q1, so I put another vertical bar there. Then 72 was the median. 72.5 was the Q3, and 76. Then you connect the middle three with the box. There's your box, and these lines go out. Those are your whiskers. So these are the men. For the women, do the same thing. The smallest value is 69, so that's right here. Then the Q1 is 74. The median is 78. 79.5 for Q3, and 81 for the max. So their box and whisker looks like that. So use the 5 numbers to get the vertical bars, and you box the middle 3, whiskers come out. Okay, Mr. Funderburg gives a 10-point quiz and records the scores in the frequency table. Find the 5-number summary and identify any outliers. So we have a total of 1, 2, 3, 4, 5, 6, 7, 15, 16, 17, 18, 19, 22, 25, 26, 27, 28, 29, 30. So there are a total of 30 scores. So we need halfway between the 15th and 16th number. Now these are already in order, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the 15th number is going to be a 7. The 16th number is going to be a 6. So halfway between 7 and 6 is 6.5. If you wanted to, you could list them out. You could do 10, 10, 9, 9, 8, 8, 8, and then list 7, 8, or 8 sevens, 4 6s, so on and so forth, until you got the full list of 30. Or you can just count. So there's our median. So let's see here. So that's going to be in the middle. The lowest score is a 0. The highest score is a 10. So let's see here. So since there's 15 values in each half, the 7th value is going to be the Q3 here. So 1, 2, 3, 4, 5, 6, 7. So, oops, that's going to be 8 up here. 1, 2, 3, 4, 5, 6, 7, 4 down here. Okay, so the 5-number summary then. There's your 5-number summary. So the interquartile range is 8 minus 4, which is 4. 1.5 times 4 is 6. So there are no outliers. So because 6 plus 8, it would be 14, and 10 is the maximum. 4 minus 6 is negative 2, so there's nothing outside of those values. So anything greater than 14 or less than negative 2 would be an outlier. 8 plus the interquartile range, 4 minus the interquartile range, or 1.5 the interquartiles. So there you go. Okay, so here we've got the mean. So the mean is the average of the numbers, add them all up, divide by the numbers in the list. Calculate the mean annual home run total for Roger Maris's career. So you'd add up all the numbers and divide by whatever that was, 12, 15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 14 plus 28 plus 16 plus 39 plus 61 plus 33 plus 23 plus 26 plus 8 plus 13 plus 9 plus 5. Divided by 12. So he averaged, let's see here. I think I missed a number somewhere. I did, because I did 128 instead of 28. So I got a number that's way too big. $275 divided by 12. So the average here is 22.9 home runs a year. So unlike the median, the mean is not a resistant measure of center, which means that very large or very small values can throw off it, which are outliers or skew the graph. So the table below represents the frequency table of Mr. Funderburg's quiz scores. Compute the mean score, compare it. So what we can do is what's referred to as a weighted average. So where we just multiply each score by the number of times it appears instead of adding 10, 10, 9, 9, 8, 8, 8, and then so on and so forth. We can do 2 times 10 plus 2 times 9 plus 3 times 8 plus 8 times 7 plus blah, blah, blah. And then divide it all by the number of scores, 30. So that's 20 plus 18 plus 24 plus 56 plus 24 plus 15 plus 12 plus 6 plus 2 plus 1 plus 0. Divide by 30. So this should be 178 out of 30, which means that the average was 5.9 points. Which is the formula I just did here. The formula for finding the mean of a list of numbers, given their frequencies, is number times frequency plus number times frequency. This X bar means the average, and then you divide by the total of all the frequencies. So how many measurements you make. Okay, now the same formula can be used to find a weighted mean, which is given weights, so like the weighted grades, things like that. So example, at Marty's school, it's administrative policy that the final exam must count for 25% of the semester grade. If Marty has an 88.5 average going into the final exam, what's the minimum exam score he needs to earn at least 90% for the semester? So he has an 88.5, and that's going to be worth 75% of his grade, plus 25% is the final exam, all divided by 1 for 100% of his grade. And he wants to get a 90 for the semester. So this would be what your setup would look like. So we can work some of this out. So 0.75 times 88.5 is 66.375 plus 0.25x equals 90. So subtract that across. 90 minus the decimal gives me 0.25x, has to equal 23.625, and then divide by the 0.25. So if he wants to get his grade up to a 90, he needs to score 94.5%. On the test. Yeah, you copied something down wrong. Yeah. So there you go. Also change depending on if his school rounds, like if his school rounds like we do, if you put like an 89.5 here, if that would be a difference. Okay, so variance to standard deviation. So the standard deviation is given by, you take each value, you subtract the average from it, you square that value, you add all of that up for all of the different values, divide it by the number of numbers in your list, and then take the square root of that. So x bar, the variance is sigma squared, which is if you just essentially don't take the square root. A researcher measures 30 newly hatched loon chicks and recorded their weights in grams shown below. Based on the sample, estimate the mean of the standard deviation for the weight of loon chicks. Are these measures useful in this case, or should we use the 5-number summary? Now, what you can actually do is you can do this on your calculator. So on the Casio, if I go to statistics, actually we'll delete everything here. Delete all, yes. Delete all, yes. So I'm going to enter my numbers going down, 79.5. 87.5, 88.5, 89.2, 91.6, 84.5, 82.1, 82.3, 85.7, 89.8, 84.0, 84.8, 88.2, 88.2, 82.9. Especially when you get a large list of numbers, a calculator will be your friend. So there you go, got all 30 numbers in. And then I can go to calculate, which is F2, and I want to calculate one variable because I only got one column, and this gives me a summary. So there's my average. X bar is the average, 87.15. Now, you have to be careful with the sigma and the S. The sigma assumes that you have the entire population. S means you just have a sample of it. So for this, the average value from my thing was 87.2. And then let's see here. Based on the sample, so we want actually SX, not sigma X, which is 30.56. So now, assuming I entered all my numbers right, these values should be right. If this was if there were only 30 loon chicks total, then I could use the sigma. But since I have a sample, I have to use the S. All right, let's see what we got next. Okay, so normal distribution. These curves are referred to as normal curves or bell curves. If the data of a population is normally distributed with mean mu and standard deviation sigma, approximately 68% of the data lie within one standard deviation. If you go out to another standard deviation, you get 95%, and out to 3, you get 99.7%. So example 11, based on a research data presented in example 10, would a loon chick weighing 95 grams be in the top 2.5% of all newly hatched chickies? So let's see here. Okay. So top 2.5% would be, I want to find the 95%, because if it's 95% the data lie in between, that means there's 2.5 in the top and 2.5 in the bottom. So it had to be more than this number, average plus 2 sigma. So my average, oh, did I lose my paper? Was 87.2, plus 2 standard deviations was 3.56. So 87.2 plus 2 times 3.56. So this would be 94.32. So 95 is more than that, so yes, it would be. Because that'd be the cutoff. Anything below that would be inside the 95%. So we want it to be more than that number. And that is the end of the section.